Hello friends, continuing with the chapter of current electricity. Today we come to fifth part of mind map as shown initially at the beginning of this chapter, that is Kirchhoff's laws. Today's topic is Kirchhoff's laws. Introduction. Kirchhoff's laws are more comprehensive than Ohm's law. These are used for solving problems concerning electrical network which may not be readily solved by Ohm's law. Kirchhoff's laws are useful particularly, number one, for calculating the current flowing through various elements of the circuit, and number two, in determining the equivalent resistance of a complicated network of conductors. I repeat, Kirchhoff's laws are more comprehensive than Ohm's law. These are used for solving problems concerning electrical network which may not be readily solved by Ohm's law. Kirchhoff's laws are useful particularly, number one, for calculating the current flowing through various elements of the circuit, and number two, in determining the equivalent resistance of a complicated network of conductors. We have two Kirchhoff's laws. First is current law and the second one is voltage law. Now we take up first the current law. It is also sometimes called as point law or junction law. Now the statement. In any electrical network, the algebraic sum of the currents meeting at a point is always zero. I repeat, in any electrical network, the algebraic sum of the currents meeting at a point is always zero. Now look at the complicated circuit as shown in diagram. It has three resistances R1, R2, R3 and two batteries with EMF E1 and E2. So it is difficult to solve this circuit with Ohm's law. But with Kirchhoff's law, we can solve such a circuit. Now for current law, what are the sign conventions? Now sign conventions for current law are as follows. Currents entering a point are taken as positive and leaving the point are taken as negative. So we can take the reverse of it also. Sometimes the current entering a point are taken as negative and leaving the point are taken as positive. But that we are not going to do here. Here we will do what we have written here, that currents entering a point are taken as positive and leaving the points are taken as negative. For example, consider point C in the network. For this point in the network, we see that I3 is entering the point C and I1 is leaving the point C and I2 is also leaving the point C. So how we write the equation, current equation, as I3 minus I1 minus I2 equal to 0 as per sign conventions. I repeat, for point C, how we write current equation, that I3 minus I1 minus I2 is equal to 0 as per the statement of the law. It is algebraic sum of all the currents meeting at a point is 0. Okay. Or in a simplified form, we can write summation I equal to 0 at a point in an electrical network. So this is how we write current equation for a particular point, as we have written here for the point C. So we write I3 minus I1 minus I2 equal to 0. Now 2, voltage law or mesh law. Now statement. In a closed loop or mesh of electrical network, the algebraic sum of the products of current and resistance plus algebraic sum of EMFs is always 0. I repeat, in a closed loop or mesh of electrical network, the algebraic sum of the products of current and resistance plus algebraic sum of EMFs is always 0. Now mathematically, we write voltage law as summation I into R plus summation EMFs is equal to 0 in a closed mesh of an electrical network. Now, sign conventions for voltage law. While going round the closed mesh, fall in voltage is taken as negative and rise in voltage is taken as positive. You can take the other way also. While going round the closed mesh, fall in voltage is taken as positive and rise in voltage is taken as negative. But we are not going to use that sign conventions. Here what we have written in words, we will follow that. So we have written in words that while going round the closed mesh, fall in voltage is taken as negative and rise in voltage is taken as positive. Now how we find out the fall in voltage or rise in voltage, let us see. Now since we know where electron enters the resistance, that end is taken as negative, and where leaves, that end is taken as positive. And electrons flow in a direction opposite to flow of conventional current. Thus, entering point of conventional current is at higher level and leaving point is at lower level. Therefore, there is fall in voltage as we go from higher, that is entering point, to lower level, that is leaving point of conventional current. So here, if we look at this circuit diagram, this point is at higher level and this point is at lower level. Similarly, for R2, this point is at higher level and this point is at lower level, because conventional current enters at from R1 side and leaves towards point C. Okay, similarly with other resistances you can mark plus minus. Now using sign convention, let us write the voltage equation for particular mesh. For example 1, consider closed mesh A, B, D, C and A. The voltage equation for this closed mesh can be written as minus I1 R1 plus E1 minus I3 R1 minus I3 R2 equal to 0. Let us mark it as equation 1. Now example 2. Consider closed mesh C, D, F, E and back to C. Voltage equation for this closed mesh can be written as I3 R2 plus I3 R1 minus E1 plus I2 R3 plus I2 small r2 minus E2 equal to 0. Let us mark it as equation 2. Example 3. Consider closed mesh A, B, F, E, A. The voltage equation for this can be written as minus I1 R1 plus I2 R3 plus I2 small r2 minus E2 equal to 0. Let us mark it as equation 3. Now this is how we can write a voltage equation for a particular closed mesh according to sign conventions and statement of Kirchhoff's laws. Now, physical significance of Kirchhoff's laws. If one starts from a particular point in an electrical network and goes around the closed mesh, one comes back to the starting point. Then one must be at the same potential with which he has started. I repeat, if one starts from a particular point in an electrical network and goes around the closed mesh, one comes back to the starting point, then one must be at the same potential with which he has started. That is, while going down the closed mesh, net work done is always zero. I repeat, while going down the closed mesh, net work done is always zero. This is another way of explaining the significance. Now assignment 3.5. Next slide please. Assignment 3.5. Question number 1. Calculate the value of electric currents I1, I2, I3 in the following circuit. So look at the circuit. This is I1 leaving point C, I2 is leaving point C, and I3 is entering point C, and rest of the circuit is there before you. Using the Kirchhoff's laws and the respective sign conventions, you calculate value of I1, I2 and I3. So here is the answer, I1, I2 and I3 for verification. So when you solve, you can verify your results from these answers. Question number 2. A battery of 10 volt and negligible internal resistance is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors, each of resistance 1 ohm as shown in the circuit diagram. Determine the equivalent resistance of the network and the current along each edge of the cube. And here is the answer for your verification. Question number 3. Determine the current in each branch of the network as shown. And here are the answers given for your verification. Question number 4. For the circuit shown here, calculate the potential difference between points B and D. And here is the answer, VBD is equal to 0.4 volt. Question number 5. In the following circuit, calculate the value of R using Kirchhoff's laws. And here is the answer, R is equal to 1.66 ohm for your verification. Question number 6. Determine the current in each branch of the network as shown. Here are the answers given for your verification. So you solve these numericals using Kirchhoff's laws and with their sign conventions, and then try to arrive at solutions. I have given you answers for your verifications. Thank you so much. Next time we'll take up part 6 of this chapter as per mind map, that is measurement of resistance. Till then, goodbye.